so let's talk about logarithms. So I said that 5.1 and 5.2 are the two things, inverse functions and exponential functions smashed together, and that's exactly what logarithms are. Let's start with definition. So you have a base. It's just like the base of an exponential function, but we're doing the inverse function to that. It's the new thing. So for the exponential function, 1 is like not a very interesting function. It's a function 1 to the x is just 1. But for every other base bigger than 0, you get something interesting. So either get exponential growth or exponential decay. But well, let's define a logarithm in 2 steps. So we start with the function f, which is defined as f of x is b to the x. Then this tells us the definition of log base b. So this is the definition. Log base b is this new thing where log base b of x is f inverse of x. So for example, let's not start with e. Let's start with something that's more comfortable. B equals 2 is pretty nice. So just a function that keeps doubling. Well, let's start with the exponential function. So x and then 2 to the x. So we could have 0, 1, 2, minus 1, minus 2. So 2 to the 0 is 1, 2 to the first is 2. And, 2, 4, 8. And negative powers is 2 to the negative first is actually 1/2. 2 to the negative 2 is actually 1/4. And negative third would be 1/8, and so on. So the whole point is that you have a function f that goes this direction. F inverse would do the opposite. So f inverse would be a function that takes these inputs and gives you these outputs. So this could be, from the perspective of the function f inverse, these are the x values, those are the inputs, and these are the outputs. So this is, if this is x, then the output is f inverse, which is, this is the thing called log base 2. So just like squaring is the inverse of taking the square root, it's like the, you undo the exponential function. So, well, 8 is 2 cubed. So yet another way of thinking about this that's often really handy. If you can write something that's 2 to the something, then the logarithm is right there in the exponent. That's what's cool about this. So it's 1/4. Well, the base is 2, so I want to write it with base 2. The logarithm, exponential function 2 to the x takes the number on the left and gives you the number on the right. Going backward, if I write everything as 2 to the something, then, well, 8 doesn't, if I just look at the number 8, that doesn't tell me what log base 2 is, but if I write it as 2 to the third, awesome. So that's how that works. So if you read this table from right to left, you get the log table. So let's just straighten that out. So if I call these x's and I call these y's, and I write it in the standard order, so just flip it. So what power of 2 is this? It's the negative second power. What power of 2 is this? That's the negative first power. 1 is the 0th power of 2. 2 is the first power. 4 is the exponent is. Log just sort of just tells you what the exponent is. So if I have an exponent, then this is how algebraically, if you happen to see a number and you recognize that it's already a power of the exact same base, if you can write it that way, then you've got it. You just cancel log base 2 of 2 to the something, it's just the something. Log base 2 of 2 to the m is m, and that's it. So another one, you don't see this one quite as often, but this one is also true. These are kind of like which function you put on the outside, which function that you put on the inside. Well, the function and its inverse, they cancel each other. Those are the two inverse properties. And just whatever the base is. So for that's what it is for log base 2. But for any log base b of b to the something, so it's this one has to match for it to work, and then you're good to go. So just be careful about this. Just make sure that these have to match. So this is bad. This isn't anything at all. This is just, it's a number. Whatever the number is, it's some random decimal. There are ways to compute it with a calculator, but you have to know the right keystrokes. But these two are the ones that are nice and convenient, standard. Anytime you can do this, this cancels these. It's the same function and its inverse function, but this is a base 3 logarithm with a base 5 exponential. So that's how you know. It's the base of the exponential function has to match the base of the log. So this is nothing. It's not anything. It's just some number. It's not anything nice. It's not a whole number. It's just some whatever it is. It's some number. And so I want to get that out of the way. I want to go now. Let's run through a few more. There are some book problems where and some MyLab. The MyLab test wants you to sort of get in the habit of doing this. So, for example, they say so these are these look a little bit goofy the first time you see them, but once you know what to do, it's pretty simple. You just have to sort of get used to understanding what they're asking for. Well, they'll give you in a statement like 2 to the 5th is equal to 32. Well, that's an exponential statement, and we just use the inverse. I think I did that right. 2, 4, 8, 16, 32. Yeah. Okay. So this is the final answer that they're looking for this kind of problem. They just want to say that they just want you to say that log base 2 of the simple number is equal to whatever the exponent is. So you just take log base 2 of both sides and you cancel it. And that's all they're looking for. So if they say that e cubed is, well, I forget what that is. So it's 20 something or 30 something maybe. Something like that. Anyways. So if they just, if someone computes this for you, and here, let me introduce this brand new thing. This is it's letter L, and sometimes you see a curly L in these logarithms instead of a straight L, because straight L looks kind of like a 1. But I'll try to be consistent and just do this. Maybe I'll make a note over here. Standard basis. It's just a so yeah, so for this book and a lot of math books, you'll see these so sometimes in other books, like the farther you go in math, the less you see log base 10, and the more that they use both of these just to mean log base e. But it's pretty common that you'll see this. So log base 10 is usually just called plain old log. Log base e is just called natural log, or that's what or log natural. It's written to ln because the adjective goes after the noun in French, and I think this was just the standard, what we, the notation that we use for logarithms was sort of invented in France, a couple hundred years ago, and I think it was the 1800s, something like that. Okay, so in the book, even though e cubed, how do you write e cubed is equal to, someone computed it for you, well, how do you write that as a logarithmic statement? That means that 3 is the natural log of 20.086 and so on. And this log base e that's mathematically correct, but it's not the standard way of writing it. The standard way of writing it is it's very, very, it's customary to take your log base e and rewrite that as ln. All right, so that's so one more here. So just 10 to the 6th is equal to all this nonsense here. So 1 million over 1 6 zeros. Oops, I forgot to leave room to write down the log base 10. So the left hand side, that's the inverse property, and then 6 is equal to log base 10, or I could just write log now. And I'm not sure. I think MyLab, if the base is e, it wants you to write ln, and if the base is 10, it just wants you to write log. They don't want you to specify the manually log base 10. If it's they want you to use the standard shorthand, which is this. All right, so what have we done so far? We looked at tables, but we didn't really do graphs yet. So I want to look at graphs, and I also want to look at the I also want to look at the change of base formula. It's kind of where is for the erasing? What did I do with it? space in the room. Okay. I briefly want to say why logarithms are useful, and I also want to say why are there only two different logarithms on your calculator. So the general statement looks like this. And then, well, how do you use it? Well, A can be whatever base. A and B are both positive numbers that are not equal to 1, but usually for your calculator, you want to use log 10 on the right-hand side. The one that you want to know what is log base B of some specific number that we're interested in. In applications, you'll want to use either sorry, I wrote that. Yeah, so let me. Yeah, okay, yep. So it's just log base b of x is just log of x divided by log of b, or you can use natural log. So these are the two functions that are built into your calculator. So it's only theoretically useful because if your calculator for some reason had log base 3, you would use log 3 for both of these instead, and that would be how you would push the buttons. But for applications, these are the ones that are in your calculator. So for example, you can use one of these, doesn't really matter which, just make sure they're either both log 10 or both of them are log e. You just pick one and if you try it both ways and write down your answer with log 10, and then try it again with log e, you'll get exactly the same thing. So if you have $1,000, 5% growth rate per year, how long until you have twice as much? So that would be 2,000 would be what you started with times you multiply by, you get an extra 5%. Each year you multiply by 1.05, and that many years, so you divide both sides by 1,000. And well, what you want to do here is, for this application anyway, we're going to learn more about logarithms, but this problem right here we can solve right now with just the change of base formula and what we know about logarithms. So if one side of your equation is just a standard, your basic exponential function, then that's exactly what the inverse function is for. You take log base 1.05, then the right hand side cancels, and here it's log of the value divided by log of the base. So just use something that's in your calculator and use the same, it's natural log and natural log, or whichever one you use. If you use log base 10, then both of these numbers will be smaller, but then the ratio of the two will give you exactly the same answer. So ln of 2 is like 0.7-ish, and then ln of 1.05 is 0.048 something. Let's divide those. ln of 2, if you do it in your calculator, you might want parentheses around that ln of 2. Then ln, then parentheses with ln of 1.05, it takes about 14 years. And that's what you do with the change of base formula. So it just really depends on context. It's like, usually what you want to think about is a lot of things in, bacteria growth under ideal circumstances for the bacteria. You want to think there's exponential growth, and exponential decay is like, that's what an exponential function does. It tells you how much you have. And the inverse of that is the logarithm helps you solve for t. So how long does it take is what the log is doing. So it's if the base is less than 1, then you're asking how long does it take for exponential decay to do its job. Log with the base bigger than 1 is like how long does it take for exponential growth to do its job. So so there are a few different ways of thinking about it. But here, the whole point is log helps you find the exponent. And one thing that's really interesting about log is that maybe we were really interested in log base 1.05, but how did we do it? At the end of the day, we use natural log, or we use log base 10. Somehow, if I know how to compute one of the logarithms, I always know how to compute whichever logarithm I'm interested. So they're sort of interchangeable. We just need some techniques. And the change of base formula is one very useful and productive way of going about that. So I want to look at graphs here, and it's let's go back to this side here. I do want to just do a graph, so maybe this is a good place to this table is going to help us a lot. So let's just start graphing. Okay. And what's nice about, with transformations, it's really nasty because you might be multiplying by a big number. But with just a function and its inverse, you you know, you can just use one kind of pair, just one scale will fit both of them kind of equally well at the same time. So is this one actually a homework problem? Did I give you 2 to the x? I should probably pick something slightly different. I think maybe I picked, what did I pick? Did I pick something? That's okay, maybe just this once. It's a long, some of these homework assignments are getting kind of long, so and not everybody always actually watches all these videos, so it's not like I do all the homework solutions all the time. That would be too much, but let's just do this once. This should be fine. So we have a function and its inverse function. The exponential function, we know that we go backwards in time, we undouble it as we go backwards in time. So we get a horizontal asymptote. But then if x and y swap roles because it's the inverse function, then that becomes a vertical asymptote. So let's just start with this one. So we got okay, so this, not everything's going to fit on the graph quite so easily, but let's do this. 0, 1, we got -1, 1/2, and then -2, or with +1/4. 1 gives you 2, 2 gives you 4, and then finally 3 is going to give you 8. And let me make sure I at least start labeling the scale just to give you. And if you want to have this line of symmetry, just make sure that your y and your x are labeled so that they have the same scale. So even if it, like, you don't want to have these numbers being a lot bigger than the same number because you want it to be a nice symmetric picture. You don't want this number to be 8,000 and then this number to be just 5, because then the line of symmetry gets messed up and it won't be as easy to visualize anymore. So let's just use a nice perfectly square scale here. So both horizontally and vertically, I'm counting roughly one tick is about the same spacing for both axes. And then that's 2 to the x. It's these numbers here, and then mirror image. So 0, 1 becomes 1, 0. And then -2, +1/4 becomes 1/4. And -2 is down here. And something, it looks like this here. So if I'm being very, very careful, the horizontal asymptote for an exponential is horizontal at y = 0, and then the logarithm has a vertical asymptote at x = 0. So that's kind of important. 2 to the 1 is 2, but then log base 2 of 2 is 1. So this 1, 2 becomes the green point 2, 1. 2, 4 becomes 4, 2. That one I didn't draw super duper well. If I had drawn this super duper well, this would be a little bit higher up. This would be a little bit lower down maybe. But anyways, 3, 8 becomes 6, 7, 8, 3. and this one would, yeah. So my art skills are a little bit off, but you can imagine that these would line up super duper well if I had done it slower. I think these are a little bit too close together compared to these being spread out, but if I fix that, if you turn this in, you get 100%. That's, there's the correspondence, there's the line of symmetry. You can see how it got a little bit warped, like I was saying, because I wasn't super duper careful with the scale, but it was close enough. That you should kind of get the idea here, and that's it's basically what we're looking for here. Yeah, and then if I have, let's see, did I do 1/3 already, or is that? One third is not. So this is a good example, I guess. So let's do these on the same scale, and well, usually you see ln and you see log base 10 are the ones that are most important, but this is still a perfectly reasonable math question, just to sort of get a little bit of practice, get it under our belt. We should be able to understand this if we wanted to, if we needed to for some reason. So let's go ahead and do it. So pretty reasonable question, I guess. Needs to dry just a little bit more before I can actually write on it. Let's see. Okay. Something like that. Let's 2, 3, 4, 5, 6, 7, 8, 9. That goes all the way up to 10, and that's more than enough. So let me try to keep it even here. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so if this one right here, 0, I get 1, and it gets smaller very rapidly. So if I go backwards, I get bigger numbers. So if I plug in -1, I get +3. If I plug in -2, I get 1, 2, 3, 4, 5, 6, 7. These are a little bit, yeah, they're not quite the same size. Let me fix it that a little bit. Okay, so now that's large enough that you can kind of see it. Okay, so 1/3 to the first, 1/3 squared. There's not a whole lot I can do as I go farther to the right, but I can go farther to the left, and there's still room. So 1/3 to the -1st is 1, 2, 3. 1/3 to the -2 is 1, 2, 3, 4, 5, 6, 7, 8, 9. Table is 1/3 to the -2 is, you take the reciprocal and square it, you get big old 9 here. Okay, so that's what we have to start with. I'll do the axis of symmetry. Maybe I'll use blue for the axis of symmetry. So this isn't f of x, this isn't f inverse of x, this is this geometric line y is equal to x, which is just an axis of symmetry. Reflection, or it's how the function f and the inverse function are related to each other. So we reverse the roles of x and y. We get log base 1/3 of x is the output now. So what power of 1/3 is that? That's the -2nd. What power of 1/3 is that? That's the -1st power. That's the 0th power. 1/3 is the first power of 1/3. 1/9 is the second power of 1/3. Okay, so that's -2, 9 corresponds to 1, 2, 3, 4, 5, 6, 7, 8, 9. But then down here is y is equal to -2. Yeah, so these graphs are a little bit weird because you can see that the two curves are going to cross. Both curves end up crossing the axis of reflection. So -1/3 becomes 3, but with -1 here. So we know we need to connect these two. 0, 1 is going to become 1, 0. 1, 1/3 is going to become 1/3. It's going to go all the way up here to 1. So we got to be very careful here. The green line is suddenly becoming very steep vertically. It becomes very shallow as you go this way. And then the original function, when we get 2, we had 1/9, which means when we're at 1/9, we go up to 2. And actually, remember, we had the exponential function has a horizontal asymptote, y is equal to 0, but then the log function, everything's flipped. So x's become y's, so horizontal becomes vertical, and it's not y is equal to 0, now it's x is equal to 0 for the function. So those are the trickiest ones. The logarithms with base that's between 0 and 1, those are a little bit weird, but it's a perfectly legitimate mathematical construction. You don't see them as often because usually you transform the problem so you can use natural log or log base 10 to deal with it in some way, but it's still a worthwhile thing to understand. It's just it's not the most pleasing thing on your eyeballs. You sort of have to do it very slowly and you have to think about it. It's kind of a very good starting point is just, no matter whether it's if the base is bigger than 1 or less than 1, you still have the exponential function has this horizontal asymptote in all cases, and then the logarithm has this vertical asymptote no matter what. And those guidelines, together with the axis of reflection, those three things are always going to be there. It's just the picture that you get is just a lot more pleasing with the exponential growth. This one you just have to be extra careful and then just sort of double check it, and if it doesn't look symmetric, then maybe go back and try to find a mistake, unfortunately. But this there's the picture is in your textbook if you ever need to look it up. Yeah, both of them are on page 335 for comparison. Here we did it at length with specific examples. The book kind of sketches it as a general case, but they do a very good job with that. For the homework, yeah, I'm gonna give you specific bases, and I'm gonna want you to actually graph it to scale with those. I think I asked for at least 3 sample points, but I also want the asymptotes, so you better have it approaching the asymptote that it's supposed to, and then it'll be good. But yeah, finally, I think that's everything. It's kind of a long assignment, so there were a lot of lectures, but it's worth a lot of points too. So I hope you can put the time in and get it all done. That's 5.3, so that's homework 11, all up and ready to go here.